Section 5.5, Finding Equations of Linear Models. In previous sections, we learned how to use linear regression to find the equation of a line from a couple of ordered pairs. We're going to continue to do that in this section, but we're also going to start applying that to applications a bit more, and we're going to start looking at situations where we have multiple data points that are not necessarily linear and see how it works there as well. All right, so let's jump in with an example. The number of high school students who have taken the military's aptitude test has decreased approximately linearly from 857.6 thousand students in 1999 to about 539.3 thousand students in 2007. Let's let n be the number of high school students in thousands who have taken the test in the year that is t years since 1990. All right, so part A. Let's use regression to find an equation of a linear model that describes the data. If we're going to use regression, that implies we're going to enter a couple ordered pairs. So let's go ahead and make a chart for that. So I'm going to put 3 columns in this chart. One will be the year, and then that's not really going to be our variable, so I'll also add a value of t. And then our output variable is going to be n, so I'll put that as well. So we get the ordered pairs to fill in this table from the sentences up here. So they say that in 1999, there was 857.6 thousand students taking the test. So we can fill in that year, 1999, and we can fill in the number of students, n, 857.6. That's in thousands, which we do have to remember, but we don't have to put that in our table. And then we need another ordered pair as well, and that's going to come from the fact that in 2007 there was 539.3 thousand students taking the test. So we'll add that year, 2007, and then we'll also put the number of students, 539.3. Okay, and then just one more step before we go to the calculator is we want to convert those years to values of t. T is the number of years that have gone by since 1990. So in 1999, that was 9 years later. And in 2007, that was 17 years later. And just a reminder, every time we calculate a value of t, we're taking the year that they gave us, in this case 2007, and subtracting the starting year, in this case 1990, and we get that 17. So I was doing those in my head, but if they're messier, or if you're stuck on them, you can always do it that way. Okay, now we want to go to getting the equation. So to do that, we're going to want to put our input variables into list 1 and our output variables into list 2. And then we can do linear regression like we did in previous sections. So I'm going to hit Stat and Edit. And I don't have any data there, which is nice, so I can just start in with this data, 9 and 17. And then going over to list 2, 857.6. and 539.3. And once I have those in, I'm ready to do the regression. I just hit the Stat button again, go over to Calc, and I want linear regression down there where my data is in list 1, comma, list 2. So there's the output. And I've got my slope, negative 39.7875, and my intercept, 1215.6875. And these numbers, which we'll talk about a little bit today, they tell us if our pattern is perfectly linear or not. The closer that r squared is to 1, the closer it is to a perfectly linear pattern. So when I have that r squared equals 1, I know that this is perfectly linear, and that's always going to happen when you only have 2 ordered pairs. So let's go ahead and write that equation down. If I wrote it first just using regular variables, I could say y equals negative 39.7875 times the input variable of x plus 1215.6875, and I'm just writing this y equals ax plus b form, but plugging their a in for a and their b in for b. But these aren't the equations of, or the variables of our equation, so I'll just switch that. They're using the output variable of n and an input variable of t, so I'm just going to switch those around. And that would be our equation using regression. All right, and then moving on to part B, what is the slope and what does it represent? so we can get the slope quickly. The slope is the coefficient of our input variable, so it's that negative 39.7875 number. And then what does it represent? Now we want to start thinking of it as change in output over change in input. So our output variable is n, our input variable is t. And then make that a fraction by putting that over 1. Think about the units. The bottom is change in t, and t came from 9 years and 17 years, so that's 1 year. And the numerator is the change in n, which we were told up here was measured in thousands of students, so that's thousands of students. And then I would want to move that 1,000 into the number by multiplying by 1,000. So I'll take that one more step before I try and put this into words. So multiplying by 1,000 will move the decimal over 3 spots, so I'll get negative 39,787.5 students. Now it's just students because I've already used the 1,000 to multiply in and move the decimal over, and that's over 1 year. And then I just want to put that into words. So everything so far has been scratch work. So now let's write our sentence. Starting from the bottom up, so for each additional year that goes by, so I'm just translating the denominator there for each additional year that goes by. And then the slope, the numerator part, tells us what's happening to the number of students that are taking the military's aptitude test. And that is decreasing because it's negative by 39,787.5 students per year. So for each additional year that goes by, the number of students taking this test decreases because we have a negative slope by about 39,787.5 students. And I guess we could even say per year. All right, so remember when you're interpreting slope, think of it as change in output over change in input. The scratch work I think is very helpful. Include the units in there to help sort it out, but you haven't actually answered what does it represent until you get to this sentence part. All right, and then one more piece to finish off this problem. What is the n-intercept and what does that represent? So the n-intercept is always 0 something when we have an equation in slope-intercept form, which is what regression gives us. Then this number right here would be the y-coordinate of the y-intercept, in this case the n-intercept because that's our output variable. So 0, 1215.6875. This is years since 1990, and this right here is thousands of students. And so let's see, 0 years, that's 1990, which is when we started the clock on this problem. And then if we multiply by 1,000, that will move our decimal over 1, 2, 3 spots. So now putting that into words, the model predicts that 1,215,687.5 students took this test in 1990. I do want to just emphasize real quick that anytime you get something from your equation, it's a prediction, it's not a fact. So the things we have up here at the beginning were facts about how many students took the test in those years. But now once we start using things from the model like the slope or even the y-intercept, this was not one of our data points. It's just coming from the equation, so it is a prediction that the equation is making. Okay, so that's it for that problem. All right, so continuing on to the next example, I want to go ahead and show you how we use regression when there is more than one ordered pair. So use the regression to find an equation of a line that comes close to the points in the table provided, and then verify that it's a good fit using the graphing calculator. So this is a fairly easy process. If you have multiple x values, multiple y values, you do the same thing we did above. You just put all the inputs or x values into L1 and all the outputs or y values into L2, and you do linear regression in the same fashion. You just do it with more data. So I'm going to go ahead and bring in the calculator, and we will do that process. So let's see, go into Stat and Edit, and we have some data there already. So go up to the list name, hit clear and down arrow. Do that again, up to the list name, clear and down arrow. That'll erase the old data. Put in our new x's, 2, 5, 6, 8, and 11. And our y values, 14, 10, 8, 4, and 1. And then once you have that data in, you just do the same process as before. So Stat, Calc, Linear Regression, and our data is in L1, comma, L2. And basically nothing feels different about that process. We get our slope and our y value of our y-intercept, and we can plug that into the format to get our equation. I do just want to point out that the r squared on this one is not equal to 1, and that's because this is not a perfectly linear data set. And your calculator may or may not be showing you that r squared, so as soon as we're done with this problem, I'll show you how to make sure that feature is on. You don't need it for any homework problems or test questions, but it's kind of nice just to verify whether you have kind of roughly linear data or perfectly linear data. But for now, let's write that equation down. I'll just write it down here so that we can keep everything kind of on screen. So we would write y equals, and then a, which is negative 1.5, times x, which is our input variable, plus the b, which is 17. So there's the equation. And now let's just do the other part of verifying that it comes close to the values by using the graphing calculator, and I'll also after that show you how to make sure that that r and r squared show on your calculator as well, though that is totally optional. All right, so let's see. The first thing I think we should do is set up our window. And I think it's fairly easy to set up your window when you've got data values. Go to the window button, and then think about from 2 to 11, what would we number in? What would our scale be? Probably in ones, right? Discount 2, 3, 4, and so on. So then what's a nice number below 2 that's a multiple of 1? Why not just start at 0? And then what's something a little bigger than 11 but counting up in those ones? So maybe 12, 13, something like that. I'll just go with 12. And then for the y values, same idea. If you're going from 1 to 14, I think counting in ones would be reasonable, so I'll set that as the scale. And because 1 is closer to 0 than 14, I'll start at 0. And then I'll just pick something a little bigger than the 14, but in an increment of my scale, so 14, 15, 16. I'll just go with 15. And there's my window. So I could hit graph right now, but I don't know if I'd see anything because we haven't entered the equation and we haven't made sure the plot is turned on. So to do those things, we go to the y equals menu. And none of that is currently in place, so let's enter the equation. Y equals negative 1.5 times x plus 17. Just a quick calculator note. Make sure that you are hitting the negative key on the negative 1.5, not the subtraction key. You will get an error message if you do the subtraction key. And that would give us the line, but notice plot 1, which is what we use for all our scatter plots, is not highlighted, so no data is going to be graphed. But if I arrow up to that and press enter, now that is highlighted, so now it's going to graph the line and the plot. So there's the data, there's the line, and it does look like a pretty good fit, so mission accomplished. Notice the line doesn't hit every point, so it seems to miss that one, and maybe it's not hitting that one right in the center. But that's the deal. When the data is not perfectly linear, you can't hit every point. You just try and come up with a line that does a good job of getting close to all of them. And linear regression is guaranteed to do that for you. And I'll show you why that is in a different piece of the video. Let me just show you real quick how to check the r and r squared and make sure those are on. So if you're seeing this already, you can just skip this part of the video. But if you're not, I'll show you how to make those show. So what we want to do is go down here to the catalog button above the 0 key. So I'm going to hit second and then catalog, and you'll see that puts the catalog list up there, which is in alphabetical order. We're looking for something called diagnostic on, so I'm just going to arrow down until I get to that diagnostic on, and then I'm just going to press enter right there. I'll put it on my home screen. I'm going to press enter again, and it'll say done. And turning your diagnostic on is what makes the r and r squared show. So if your calculator was not showing you r and r squared a moment ago, now that you've done this, it should be. You can hit second enter a couple times and pull back your regression and just press enter. And even if you didn't see r and r squared a moment ago, you should see them now because you've done the diagnostic on. And that's not something you have to remember either. Once you turn it on, it should stay on. Okay, so this video is just going to use this application to demonstrate to you how it is that regression goes about trying to find the best fit for a data set. So I'm going to put in a data set with 11 data values, and I'm going to have that those data values have a little bit of variation to them. Let's go ahead and get the data set. So that one's okay. Let me try another one. Yeah, that's good. So let's try and find a data set to fit this. So the question becomes, how do you find the best fitting line? So one strategy I've seen before in algebra books is they say use the point on the far left and the point on the far right, and then use your algebra skills to find the slope and to use the slope in one of those points to get the equation of the line. On this program I can roughly do that by clicking on this draw custom, and I click 2 points and that'll make the line. So I click here and then I click again there. And that does seem like it's a decent fit. But the way we measure that when we're thinking about how good of a fit it is we think about if we were to make a prediction for a point, how much of a vertical difference would there be between what the real y value is for the point versus what the line is up above. And this program can show us those errors. So if I pick a point and mouse over it, and if you look up here as I mouse over the point, it says its actual y value is 17.5. And if you took its x value and plugged it into the equation, the height of the line down here is 16.8, so that's an error of 0.7. And then what this program does, it computes those errors for every point, squares them all because the ones below come out negative, and we want to add them, but we don't want the negatives and positives to cancel out. So we square all those errors and add them up, and the sum of the squared errors for this custom line is about 10.4. So that number shouldn't mean anything all by itself, but it's some sort of measurement of how much prediction error we'd get if we use this line. So the goal is to get that error to be as small as possible. So let me remove those errors and remove that line and draw another one. I do just want to point out that there's a real risk in just picking 2 points, because what if you pick this point and that point right there? Then obviously just from a visual standpoint, that's a horrible fit for the data set. But also when I show the errors, they're really big. 427 is the sum of the squared errors. We had 10.4 a moment ago. So there's a lot of variation that you can get in how much error you get if you just kind of randomly pick 2 lines. So let me remove that stuff. And let's just draw one more. Like what if I just use this point and that point? Right, now the sum of the squared errors is 12.7, so still not as good as that first one of 10.4. So the goal of linear regression is, instead of using this point and that point, or this point and that point, or this point and that point like I did, instead of just using 2 points, linear regression uses some calculus behind the scenes and all of the data points, all 11 of them in this case, to try and make the sum of the squared errors as small as possible. So when we do regression, instead of doing this kind of custom line that uses just 2 points, we're using all the points. So this purple line represents what linear regression would do. And if we look at the sum of the squared errors for that, we'll notice that it's 9.4, smaller than the line I just drew in, the teal one, but also smaller than that best try I had before from left to right points, which had a sum of squared errors of I think 10.4. So you'll see more about this in statistics and kind of look at those errors in the process more carefully. But for right now, what you need to know is that when you use regression, you're using a process that instead of just using 2 points, uses every single one of the points with the goal of making the sum of the squared prediction errors as small as possible. And you have this guarantee from the calculus behind the scenes that if you use regression, you'll get a smaller amount of squared error with that regression line than you would with any other line that you would find. So that's why we use regression, much better than just picking 2 points. we get a much better fit, and because we're using technology, it works out to be easier anyways. Okay, I hope that kind of clarifies for you a little bit what's going on with regression. All right, now that we've kind of seen a demonstration of how linear regression works and what its goal is, let's go ahead and apply that again to an application. So airlines are scheduling flights so that more seats are filled to offset sharp increases in fuel costs. The percentage of all seats that are filled for the 6 largest airlines are shown in the table. Let P be the percentage of airline seats that are filled. So this is the percentage here, so I guess that's the variable P. In the year that is T years since 2000, well, here we have our year, but not a spot for T, so let's go ahead and add that. And then this is for the 6 largest airlines like they mentioned above. So the first thing we should probably do is convert all those values of T, or of those years, to values of T. And in this case, we're subtracting 2000, so 2001 is 1 year later, and then we have 2, 3, 4, 5, 6, 7. Kind of a nice pattern to that, but just a reminder, it's always taking the year we're talking about, subtracting the starting year. So it's not just, follow the pattern, but also all these officially come from subtracting that starting year of 2000. All right, they want us to decide on the window settings and fill those in. We might adjust these later in the problem, but we should be able to look at the data and just get a sense of how we would do that, pretty similar to what we did on the previous page. For the scale, this goes 1, 2, 3, 4, 5, 6, 7, so I think a scale of 1 makes sense. And just using the same logic as before on the previous page, since 1 is closer to 0 than to 7, I would start at 0. And let's see, for the max, just going a little bigger than the biggest, so 5, 6, 7, 8. Let's go ahead and use a max of 8. And then these are our outputs over here. And if you look at from 70.1 to 79.9, that's a distance of about 10. So I think a reasonable scale when you got that much ground to cover, which isn't very much actually, would be to number in ones. I don't think we should start at 0 though, because 70.1 is a lot closer to 79.9 than it is to 0. So we should start at something that's near 70 but below it, and a multiple of the scale. So we could go with 70 or 69. If we only went to 70, I'm a little nervous this whole point might not show up, so I think I'll use a 69. And then on the Y max, something bigger than 79.9 and a multiple of 1, so 80 or 81. Same logic as down there. If we put the 80, maybe we won't see this whole point, so let's just give ourselves a little extra space and go with 81. All right, so we got the window set up, and so we'll go ahead and create the scattergram on the graphing calculator now. So the first thing to do would be to get the data in there. So let's go ahead and hit Stat and Edit. Got some data in there from the last problem, so highlight the list, clear and down arrow erases that, and again highlight the list, clear and down arrow, enter in your input values, and enter in those percentages. All right, give you a moment to catch up there. But once we've entered all that data in, we're ready to do the regression or the scatter, whatever they want. Let's see, what do they want us to do first? The scatter plot. Okay, so we'll start off with that. So everything should be pretty much ready to go on that. Let's see, except for, we have some adjustments to make. So the plot is ready to go because we've turned on plot, but we've got an equation from a previous problem that has nothing to do with this airline problem, so we should clear that out. And then our window actually is set up for a previous problem too. So we've thought about our window, but we haven't done it yet. So let's put that in 0, 8, and 1. And then over here 69, 81, and 1. And now I think we're set up. We have our window set up, we have the plot turned on, we have no extra graphs in there. So let's take a look at our data. All right, that seems to be reasonably linear. Maybe it's flattening off there. It's hard to tell just from one data value, but it certainly seems reasonably linear in the sense that I can take my pen in here and block out all the points, and that's a roughly straight line with the pen. So fitting a line to this data set seems like a reasonable thing to do, so I'm sure they'll ask us to do that in a moment. So let's see, create a scattergram on the graphing calculator. I guess we'll just put a check mark there because we did that. And then let's see what's next. Use regression to find an equation of a linear model to describe the data. So we've got a ton of space here. We really don't need that much. We'll write a y equals mx plus b version, and then we'll convert it to our variables, which will be a p equals version. And everything's kind of ready to go already. We just need to press the buttons and see our equation. So stat, calc, linear regression. Our data is in L1, comma, L2. I press enter and I get the equation in terms of y and x. I'm just looking here for rounding information. It didn't give us any, so we'll just put a lot of decimals on there. So let's see, y equals 1.73214 times x plus 68.3857 and then rewrite it in terms of the variable p, 1.73214, and the input variable is t, plus 68.38571. So there's our equation. They didn't say how many decimals to put. It's better to put too many than too few. Remember that rounding does bring in error. So I'm just being cautious there by putting a lot of them. And then use the graphing calculator to verify that model is a good fit to the data. So we just want to put that in with the plot. So I'm going to do that, just pointing out something else as I bring the calculator in. Notice that the r squared is close to 1, meaning there's a pretty strong or good linear pattern, but not perfect, so it's not a 1. So if we hit the y equals key, we can put in our equation, especially if I don't cover it up. We'll make it easier. 1.73214 times the input variable, which on the calculator will always be x, plus 68.38571. And if I hit graph, I'll see my data, and now I'll see the line drawn in there too. And it does in fact seem like a pretty good fit, which is what we should expect from regression. Regression's job is to find the very best fit you can for a data set. So use the graphing calculator to verify the model's a good fit. We did that, and it was. All right, so using technology to find equations is definitely handy, and it's definitely something we need to do when we have lots of data values. So here's just a reminder of the steps we went through. We want to enter the data into list 1 and list 2 on your calculator. This would be the input variable, which is in generic case the x, and list 2 would be the output variable, which generically would be the y. So get those into your calculator and then use linear regression on your calculator to find the regression equation. And just remember, when you're doing that, you're finding the best possible fitting line. Using stuff that we learned by hand, we could pick 2 points and get an equation that was maybe okay for the data, but when you use regression, you're using all of the data and you're getting not just a decent line, but you're getting the best possible line for fitting that data. So that's important to remember. All right, let's go ahead and look at one more example of doing linear regression to model a real-life data situation. So the table shows world record times for the men's 400-meter run. We're going to let R be the record time in seconds and T be the number of years since 1990. So filling in those variables, R they said is the record time, so that's here. And then T actually isn't anywhere on this table, so I'm going to go ahead and squeeze that in right here. And T is the number of years since 1990, so I just want to subtract 1990 from all of these. 1900, sorry. 1900 minus itself is going to be 0. This is 16 years later. 28, 32, 41, 50, 60, 68, 88, 99. Okay, so there's our values of T, there's our values of R, and we're going to be able to use that to get a linear model using linear regression eventually, but let's go ahead and look at what they want us to do. They want us to decide on window settings. We can go ahead and do that initially. We might change it a little bit later. Let's see, for the inputs, which will be the X stuff, we're going to use T. That goes from 0 to 99. I don't think I would use a scale of 1. That's just too far. 0, 1, 2, 3, all the way to 99. Maybe we'd go in tens there. And I think you always want to think about your scale first, because your x-min and x-max for a good graph should be a multiple of your scale. So we could start at 0. I always like to give myself a little extra room, so if I go below that by a multiple of the scale, maybe starting at an x of -10 would be nice. You could start at 0 too, but I kind of like having a little extra room. 99, the next multiple of the scale after that is 100. If we wanted to give ourselves a little room, maybe we could go 110. And then for the y-min and y-max in scale, let's look at that. So let's see, going from 43 to 47, we definitely don't want a number in tens. Maybe even going in ones, it kind of gets us there too fast from 43 to 47. That'd just be 4 notches. How about if we make a scale of 0.5? So that way we'd have about 8 notches or so to get from here to there, maybe 9. All right, and then we definitely don't want to start at 0. 43.18 is much closer to 47.8 than to 0. So a multiple of a half that's lower than this number, I think, would just be a nice clean 43 for a minimum. And then higher than 47.8, but still on that scale of a half, which would be like a 47.5, too small. And then 48, 48.5. I think 48 will probably work. If we don't like the way it looks, we can change that to a 48.5 later. All right, they ask us to create a scattergram for the data, and they've given us a grid, so I guess we'll do it on there. So let's go ahead and do that, and we'll do it on the calculator too, but first we'll do it by hand, and then we'll see if we can replicate that on the calculator. It might be that we end up doing our numbering slightly different on here than we did over here. That's okay, as long as we're using reasonable choices both times. So draw our axes in. The horizontal this time would be the input of t, and the output would be the world record time, so that would be an R. And then thinking about scale, the way we do by hand is a little bit different, but it is similar. So let's see, thinking about t, we want to get to at least 1999, and we're starting at 0, essentially, the way I've drawn the grid. So 99, my max, divided by the number of squares I have, is a trick for figuring out scale. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 99 divided by 14, round that up to something nice, that would be 10. Notice that that is the scale we chose before as well. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And we've got a little extra space because we rounded up a bit, but that allows us to look off into the future for maybe a world record that is higher or lower down the road. All right, we decided to break scale, I would argue, when we said we were going to start at 43, so I'm going to put a double slash mark there. And we said we were going to use a minimum of 43, so I'll go ahead and stick with that. Actually, because of some things that come up down, well, yeah, that's fine. We'll do the 43. Okay. We said we were going to use a scale of a half. Let's just see if that makes sense on here. So I would take the max, 47.8. I would subtract what I'm going to use as the min, 43. And then I would divide that by the number of squares I have left. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.48, round that up to something nice. Notice that 0.5 is going to work out pretty good there. So 43, 44, 45, and so on. Remember, our scale is a half. That's why we go up a whole number every other one instead of every one. Again, that's going to spread out our data pretty nice, I think. So now we can go ahead and start plotting that. So over 0 up to 47.8. This is 47.5, so 47.8 maybe about here. Over to 16 and up to 47.4. So maybe about there. Just doing a rough job on both of them. Here's 10, there's 20, so 16 is a little more than halfway across. 28, not quite to 30, and right at 47. So that would be here. I'm just going to keep going like that. So 32, 46.2, when something goes off pattern, that always kind of strikes me. So it looked like the pattern is going to go like this, and all of a sudden there's a big dip. So good for Bill Carr. Apparently he really broke the record by kind of more than we would have expected. And then in 41, it's 46. Notice it's starting to level off back kind of closer to that other pattern there. In 50, it became 45.8. In 60, 44.9. There's another big drop, right, compared to where the pattern seemed to be going. In 68, 43.86. It's another big drop. The other thing you might notice right there is they started going to 2 decimal places on their timers, which they still do. And then 88 would be 43.29, maybe about there. And then 99, 43.18, just a little bit lower. Okay, so there's our scattergram. All right, so the expectation was to do that by hand because we have the chart right there. But I think it also makes sense, since we've already entered everything into the calculator, to have a look at it there as well. So let's see if we can go ahead and duplicate that picture. So let's see, stat and edit. We have the data in there already. Let's see, nope, that's old data. So let's enter the new stuff in here. So clear and down arrow, clear and down arrow. So I'm going to enter those values of T into L1. And then enter those world record times into L2. And then make sure our window is set up correctly. So for our window 0 to 8 is no good. We could use what we did here, -10 to 110 with a scale of 10. That'd be okay. But in our picture, we put a max of 140, so I might as well match that. It's easy to adjust, so let's just do that. For the Y minimum, I'm going to go from 43 to 48, numbering in a halves. Though I would argue if we really want it to match, since this is 44, 43 and a half, 43, this would be like a height of 42 and a half. So let's go ahead and adjust that to 42 and a half. These are minor, but if I want it to really match between what we did by hand and what we're doing on the calculator, I'd like to line up those grids as well as possible. And then just let's see what's going to plot by hitting y equals. We have an equation, which is from a previous application, so I'll clear that out. And our plot is turned on, which is good because we want to see a scatter plot. So we hit graph, and we see something pretty similar. We don't see the axis drawn in because we don't have a height of 0 showing on there. But it does look like a pretty good similarity. We got those 3, then the drop, and then 3, and then kind of a steep drop, and then a little level off there. So it looks like we did a pretty good job by hand compared to what we're getting on the calculator. All right, next step, find an equation that models the data well. And I think a linear equation makes sense given that there's a roughly linear pattern. Not a perfectly linear pattern, but can bring the pen in there and cover up most of the points. So that means it's at least roughly linear. So we're all set up to find that because we've got all the data in there. So we just hit stat and calc and linear regression. And which points are we going to use? If we pick 2, we do okay, but if we use all of them, we do best, and the only way to use all of them is to do linear regression. So linear regression, L1, L2. Definitely not a perfectly linear pattern, so we notice our R squared is 0.96. I don't know if you noticed this kind of detail or not, but this is a little messier pattern than before, and our R squared is a little further away from 1. That is something that will happen. So let's write our equation down. Again, no rounding information from them. So I'm just going to write a lot of decimal places. I don't have a lot of room, so I'm going to go straight to the proper variables. R is our output. and our slope is negative 0.052622 times our input variable, which is t, and then plus the y-intercept number, which would be 48.0794. So that's probably enough to do what they want us to do. I think before we do anything else by hand, let's go ahead and throw that into the graphing calculator as well. So I'll hit y equals and enter that for y1, negative 0.052622 times x for the input variable plus 48.0794. And now we have the plot and the equation, so if I hit graph I should see how well that fits, and it does seem like a pretty good fit. Not perfect, but you can't fit that perfectly. It's not perfectly linear. So this is very normal that when we have data that's not perfectly linear, we're finding a data model that fits well but not perfectly. Alright, so use your equation to estimate the record in the year 2014. So the first thing I'd want to do is think about t. If the year is 2014, then t is 2014 minus 1900. So t is 114. So then I'd want to plug that in for t right here. So the record would be negative 0.052622 times that input variable of 114, and then plus 48.0794. And let's see what we get. So negative 0.052622 times 114 plus 48.0794. And our estimate is 42.08. There's no rounding directions, but given that the most recent times were given to two decimal places in our table, I think we should do that here too. Who knows? Well, no, that year has come and gone already, and they do still use just 2 decimal places. So that'd be 42.08 seconds would be our estimate. All right, I'll show you how to do that on the graphing calculator too, but let's go ahead and interpret the slope first. So slope is always change in output variable, which in this case is r, divided by the change in input variable, which is t. So let's write our slope. Where's our slope? In front of the t variable, so negative 0.05, let's just go a few decimal places, 2 over 1. Time was measured in years for t, and this was a time also, but it was the world record time, which was measured in seconds. So for every additional year that goes by, we would expect the world record time in the men's 400 meter to decrease by 0.052 seconds. So let's write that out. All right, so for every additional year that goes by, we expect the world record time in the men's 400 meter race to decrease by about 0.052 seconds. And just to point out a few things, one of which would be that I don't put the negative into my sentence as a negative, but I put it in there by saying that the world record time is decreasing. Another thing that's worth mentioning is that it may look like this data set is out of date, but it turns out that no one had broken the record for the 400 meter at the time of the writing of this book. And in fact, that was just broken, at least as of when I was doing this video. In 2016, Wade Van Nikert, maybe. Apologies for the possible mispronunciation, from South Africa in the 2016 Olympics. So that was 116 for T. Got a time of 43.03. So kind of interesting to note that that happened in 2016, and that's substantially slower than what we would have predicted for 2014. So it could be that our model is starting to break down. Maybe we're reaching the limits of how fast a human can run. This model has to break down at some point, because if you just kept going in this linear pattern, eventually you'd get to a negative time, which doesn't make sense. And so maybe it's starting to level off here, because at 2016 we're still above 43 seconds. So it might be starting to flatten out there. All right, let's go ahead and finish this off with just some quick tricks on the calculator. So I want to go ahead and show you something that we can do to store this automatically. So I'm going to clear out the equation. I'm going to go back to the home screen, and I'm going to do the regression again. So I'm going to hit Stat and Calc and Linear Regression. I'm going to do L1, L2, so that's all normal. But if you do an extra step, you can have it store the equation directly into Y1 for you. You just have to tell it where you want it stored. So you hit this variables key right here, VARS, and we're going to store it in a Y variable. We're doing function type work right now, so we'll enter it in as a function, and Y1 is where we want it to go. So if you get that comma Y1 on there and you press enter, get all the exact same output that you did before, but if you hit Y equals, you have the equation already typed in, and typed in with every decimal place that the calculator has in its memory for this. So it's a really, really accurate version. And then one other trick with that, if you have the data graphed and you have the line graphed, then you can make your predictions show up on here. Now, when we went to make our prediction for 2014, we got a time of 42 seconds. That's a little bit of a problem with our window because we didn't go that low. So let me drop the window down to like 41 seconds and graph it again. So the great part about the graphing calculator, if you want a different window, you can just make it happen real fast. It's not a lot of extra work. And then if you hit trace and make sure that you're on the line, if you're anywhere on that line and you just type a number like 114, it'll take that number and it will plug it into that equation. So if I do that, I get the 42.08, which notice was the same as our prediction here for 114. So that's kind of a neat trick. If you can store your equation into Y1, then when they ask you to make a prediction, as long as you're in the trace mode, you can just type that number in and then press enter, and it'll plug into the equation for you. So nice little trick. Use that if you'd like. All right, that wraps up section 5.5.